Welcome again. Today we will discuss titanium based organic reagents. So, titanium is a transition metal. This is 4 series. So, it is 4s2 and 3d2. So, this is titanium here after scandium, and this low valence titanium, that is very much useful for the generation of small rings. So, that is why it is called Lord of the Small Rings, and it was in this German journal Nachrichten aus der Chemie 2004 52805. So, first we will discuss summary of titanium reagents. So, Ziegler-Natta catalyst, which is Nobel Prize, so that we will discuss. Then the general preparation and reaction of titanium complexes, the metallative Rape reaction, reactions with nitriles, reactions with imines, then Kulinkovich reaction, ligand exchange of titanium cyclopropanes with other added alkenes, asymmetric Kulinkovich reaction, intramolecular variant, demeasuring modification, access to cyclopropyl amines, that we will see with amides. So, this is with amides. Then reactions with nitriles, and lastly we will discuss reactions of titanium 3 and titanium 4 complexes, nucleophilic addition to aldehydes, McMurray coupling, Tebe reagent and Neff reaction. So, first we will tell some things about organotitanium compound. So, British pastor William Gregor discovered titanium in 1791, and this is first row transition metal that we have seen earlier, and the electronic configuration is argon 3d2 4s2, and common oxidation are +2 +3 +4. These are highly oxophilic and highly resistant to corrosion, also high strength to weight ratio of any metal. In unalloyed condition, titanium is as strong as some steels. Most common use of titanium oxide in paints and sunscreen, used to make surgical implants. Titanium oxidizes immediately on exposure to air, forming passive oxide coating. And these are common titanium complexes used in synthesis: titanium tetrachloride, which is colorless liquid, and titanium tetraisopropoxide, which is also colorless liquid, and titanosin dichloride Cp2 titanium Cl2. This is bright red solid. This is commercially available. And this is precursor for Tebe reagent. You can prepare Tebe reagent from this titanosin dichloride. So, first we will discuss Ziegler-Natta catalyst, named after Carl Ziegler and Jules Natta, is a catalyst used in the synthesis of polymers of 1-alkenes, alpha olefins. Two broad classes of Ziegler-Natta catalysts are employed, distinguished by their solubility. So, one will be homogeneous, another will be heterogeneous. Heterogeneous supported catalysts based on titanium compounds are used in polymerization reactions in combination with co-catalyst organoaluminium compounds such as triethyl aluminum. This class of catalyst dominates the industry. On the other hand, homogeneous catalysis usually based on complexes of titanium, zirconium, hafnium. They are usually used in combination with a defined organoaluminium co-catalyst, methyl aluminoxane or methyl alumoxane MAO. So, this is the reaction. If you have a terminal olefin with Ziegler-Natta catalyst, you get a polymer. And as I said earlier, the 1963 Nobel Prize in Chemistry was awarded to German Carl Ziegler for his discovery of first titanium based catalyst, and Italian Jules Natta for using them to prepare stereoregular polymers from propylene. So, now we will see the mechanism of this Ziegler-Natta polymerization reaction. So, this is the starting material Cp2 titanium Cl2. This is commercially available. Now, if you react with this aluminum methoxyren, then you get this chlorine is replaced by methyl groups, and now the activation can be done on this complex and you get a vacant site, because this can eliminate as a methane actually. And then C2H4, so this is ethylene. Ethylene comes and ethylene binds to the titanium, and now migratory insertion happens. This methyl group goes to the double bond, a propyl group is generated and also a vacant site. Now another molecule of ethylene can take up this vacant site, and again the migratory insertion will happen. This propyl group adds to the olefin, you get this, again a vacant site is generated, and like this way you get this one, polymerization, and with a olefin here, ethylene, and finally what will happen, this will go to a double bond. So first this vacant site will be taken up this hydride and you get this one and the olefin, polymerized olefin. General preparation and reactions of titanium 2 complexes. So this is very important. Titanium 2 chemistry, titanocyclopropane or titanocyclopropene, that we will see. Like isopropyl magnesium chloride, 2 equivalent of titanium is added to an ethereal solution of titanium isopropoxide and acetylene at minus 78 degrees centigrade, and the mixture is then started at minus 50 degrees centigrade. The reaction most likely proceed via ligand exchange reaction between a low valent titanium alkoxide and an acetylene. So this is the preparation. So isopropyl magnesium chloride, this mechanism we will see later also. So isopropyl magnesium chloride and ether and titanium isopropoxide, then you get this titanocyclopropane. Titanocyclopropane. Because 2 equivalent of isopropyl, so this will form O isopropyl, and isopropyl group here and here isopropyl group, and then one isopropyl group will eliminate and generate this one, titanocyclopropane, which will be in equilibrium with this. And now if you react with an alkyne, the ligand exchange will happen. Now if you react with an alkyne, this propylene will eliminate and you get this titanocyclopropene, you can tell this titanocyclopropene. So this is formed, and this has been exploited in many reactions, like this one. This is 1 to bis dianion equivalent. So this, because carbon titanium bond you can break it, if you put suitable electrophile like E1 you can put here, and another electrophile AI2, di, tri or tetra substituted alkenes you can prepare, and this follows by this intermediate. Suppose if you react with an electrophile, then this kind of 5-membered intermediate is formed. So we will see details. First we will discuss this one, alkyne titanium O isopropyl to reactions. So suppose this TMS and disubstituted alkyne, if you put with titanium diisopropoxide 1.2 equivalent, 2.5 equivalent of isopropyl magnesium chloride at minus 50 degrees centigrade, you get this titanocyclopropene. Now if you react with secondary butanol, S-butanol, then 1 equivalent minus 50 degrees centigrade, you get this, and which in situ if you treat with iodine, then you get the this one is substituted with iodine, you get this one vinyl iodide, and you can react with an aldehyde also, then you get this allylic alcohol. So this is the chemistry, that alkyne can be reductively converted with titanium reagent to generate this, and then you can do a substitution reactions here or addition reactions with iodine as well as benzaldehyde to get these products. Also you can do copper chemistry. So then this is actually 1,2 addition reactions, like also you can do 1,4 addition, like if you react with cyclohexenone, then this group is coming from here and this is the 1,4 addition, you get 53% yield. Also if you react with this allyl bromide, then a substitution reaction. So this is substitution reaction is happening here. So this group is coming from the titanium part, and this is the product is forming actually. This was published in JACS 99. Cyclotrimerization reaction, that is called metallative Reppe reaction. So that is also exploited with this, and here in this metallative Reppe reaction we will see 3 different alkynes are used. 3 different alkynes are used and you can get benzene derivatives. So this is an important reaction. 3 different unsymmetrical acetylenes and 1 molecule of a certain metallic species, which is titanium in the present case, are combined together in highly controlled manner to give directly aromatic organometallic compounds as a single isomer. Like here, this is disubstituted alkyne, and if you treat with titanium isopropoxide 1.2 equivalent, isopropyl magnesium chloride 2.5 equivalent, you get this titanous cyclopropene. This then reaction with this terminal alkyne here and ether minus 50 degree centigrade. Here what happens, this carbon titanium bond breaks fast, so the addition happens here, and this is quite reduced selectively as you can see. So this adds here and like this. So you get this 5-membered titanocyclopentadiene intermediate, and now again if you react with this sulfonyl alkyne, then this is the selectively this compound is formed. The detailed mechanism we will show in the next slide, but if you see the reduced selectivity here also, this bond is breaking and this is adding to here. And this intermediate, if you put with iodine, then you get this iodobenzene. So this is iodobenzene is formed with substituents also. Alternatively, this one, if you react with benzaldehyde, what happens? This reacts with the carbonyl group and that oxygen cyclized with the ester, so you get a lactone here, and this compound is formed in 49% yield. So this is very useful reaction, and you can see the all alkyne component are present. This was blue, then red, and the green, all alkyne component are. So this is an useful reaction. So what could be the mechanism? So this could be the mechanism that this, the last step actually, the sulfonyl alkyne, that mechanism we will see. So this one was formed titanous cyclopentadiene 4, and if you react with sulfonyl acetylene, then you can think of a 4+2 reaction. This bicyclic intermediate might form, and then this one is formed, and this, if you see this one, this carbon titanium bonds breaks, and now the olefin will isomerize, and you get this one, and after that elimination of SO2 toluene group, you get this 6. Alternatively, so this titanocycle, the carbon titanium bond of the titanocycle 10 rearranges to a suitable position such as 11, where the 1,2 elimination of the sulfonyl group is feasible. Finally, the sulfonyl group was eliminated to see the equilibrium for the formation of aryl titanium compound 6. So this is aryl titanium compound that we have seen earlier. This aryl titanium compound will form. Alternatively, the insertion reaction also is possible, like this one reacts with this and you get a, this is insertion, and then a rearrangement happens to get this aryl titanium benzene derivative. So with this we can develop also facile preparation of various heteroaromatic compounds as a titanocyclopentadiene intermediate. So this cyclopentadiene intermediate, if you generate as a titanocyclopentadiene intermediate, then it will be also useful, and that is possible only with reaction with nitriles. So this alkyne is there, and then instead of other alkyne, here we have put the nitrile, and this is the intermediate. Earlier it was carbon here, so here it is as a titanocyclopentadiene. So as a version this one, and this also has been useful. So if you react with the sulfonyl acetylene, you get pyridine. So remember, this nitrogen is here, so that is why the pyridine derivative is formed, and the mechanism will be similar, we will see in details also. And if you put another equivalent of nitrile, then you can get pyrrole. If you put an aldehyde, then you get furan. This is furan, and if you see this R4 is here, so it is substituted furan. Alternatively, if you put this intermediate just with H plus, then the hydrolysis of imine is happened, and you get this alpha beta unsaturated ketone. Alpha beta unsaturated ketone. So alpha beta unsaturated ketone is formed. If you don't put another electrophile, then you get this ketone. And this work was published in JACS 2006. So we will discuss first the mechanism of the formation of pyridine, where the sulfonyl alkyne was used. Sulfonyl acetylene 14 was incorporated in the as a titanocycle 7 in a regioselective manner to give intermediate 16AB. So first this is formed, we have seen earlier, the as a titanocyclopentadiene will be formed with titanium isopropoxide, 2 equivalent of isopropyl magnesium chloride minus 50 degrees centigrade with alkyne and an nitrile. After this you put this one, and now this 4 plus 2 will happen, and now this will be formed, and this 16A which will be converted to 16B like earlier we have seen. And now the elimination of SO2 toluene group, so this is the elimination. SO2 toluene group will this titanium metallated pyridine derivatives. So this way the SO2 toluene is eliminating, this bond is in nitrogen titanium is breaking, and you get a double bond, that is the aromatization also. So this is aromatization is happening here, and you get this titanium carbon bond here, which can be of course protonated to get this pyridine compound. For the furan formation, we have seen that you have to use another aldehyde. So as a cyclopentadiene 7 generated from 4 and 6 was added benzaldehyde, and the reaction mixture was gradually warmed to room temperature to give ADAC 48. So this was the common intermediate as a titanocyclopentadiene, and now if you react with benzaldehyde, and here the benzaldehyde will add to this carbon titanium bond, because this is more reactive. So this bond will break and the benzaldehyde will come. So this is the benzaldehyde substituents here, and benzyl group is here, benzaldehyde after addition. And now if you put the acid, what will happen? This alcohol will attack to the iminium ion to generate this intermediate, and then the aromatization will happen to give this furan. So aromatization. Also one equivalent of ammonia is eliminated, as you can see the ammonia is a leaving group here. So you get a tetrasubstituted furan. So this is very useful method to generate tetrasubstituted furan, the alkyne, nitrile and an aldehyde. And now pyrrole, we have told that if 2 equivalent of nitrile is used, then the pyrrole formation happens, and this is the mechanism. The compound is most likely produced by a double addition of nitrile to the acetylene complex 5-17-21, and the resultant dititanocycloheptatine 6 was hydrolyzed to diamide 62, which underwent ring closure. So this is formed, and now 6, this is 6, the nitrile. The nitrile is 6, so after this common intermediate form, and now the nitrile again is added, 6 is again added, and selectively, as we have seen, this bond will break, and here the addition happens, and nitrile addition you get imine. So this is the intermediate diazotitanium cycloheptatine 60 is formed. So here you can see 2 imine is present, and now because this is a hydrogen is acidic, so this kind of isomerization will happen. Of course, this is happening because of aromatization, and now this enamine will attack to the iminium ion, that's what, to generate this 5-member nitrogen cycle 63, and elimination of ammonium group followed by aromatization will give you pyrrole. Pyrrole carboxyaldehyde 61 as the final product. So this is very important reaction, pyrrole carboxyaldehyde. So this is useful reaction. If you use 1 equivalent of alkyne and 2 equivalent of nitrile, then you can get this pyrrole with titanium chemistry. So this is the acid mediated here finally. Now we will see what happens with imine. So instead of nitrile, if you react with imine, then again this bond will break here. So if TMS is there, then this bond will break, and you get a addition reaction, and here you can put with iodine, then this carbon titanium will be replaced by iodine. So you get vinyl iodide, and also this is alpha beta unsaturated amine, So imine is converted to amine, and also if you put the acidic workup, then this titanium bond can be break. Alternatively, you can put carbon dioxide, then you get a amide, cyclic amide, which is called lactam. So formation of lactam is observed. So this carbonate group is coming from carbon dioxide, and the double cyclization is happening to get this cycle. Now we will discuss Kulinkovich reaction. This is also powerful reaction for the generation of cyclopropanols from esters. The Kulinkovich reaction describes the organic synthesis of cyclopropanols by reactions of esters with dialkoxy titanium reagents generated in situ from Gigner reagents bearing hydrogen in beta position and titanium 4 alkoxide, such as titanium isopropoxide. This reaction was first reported by Oleg Kulinkovich and co-workers in 1989. So here also the mechanism involves the titanium cyclopropane that we will see. So if you have a ester and 2 equivalent of Gignard and titanium isopropoxide, this you can use catalytic amount also 5 to 10% ether 18. So this is room temperature reaction followed by acidic workup, you get 10 to 99% yield of this compound, so cyclopropanol. And you can see this is 2 carbon homologation, because these 2 carbons are coming from the Gignard, and this is the ester part, and this carbon is this carbon. Carbonyl carbon become a this is quaternary center, this is tertiary alcohol. Tertiary alcohol is formed. Original reaction 1989 used a mixture of stoichiometric amount of titanium isopropoxide 1 equivalent, ethyl magnesium bromide 3 equivalent, and ester at minus 78 degrees to minus 40 degrees centigrade. And the catalytic version 1991 uses slow addition of ethyl magnesium bromide to equivalent to a mixture of ester and titanium isopropoxide 5 to 10 mole% at 80 to 20 degrees centigrade. So catalytic version was developed later, as you can see here, and this was the paper, initial paper, and then the catalytic version. And the scope of this reaction is very broad, different esters can be used. As you can see here, this R1 is shown in the red here, So this is the cyclopropyl ester, this is benzoate derivatives like PCOET, ethyl benzoate. This is the functionalized esters, this is also substituted ester, this is alpha beta unsaturated ester, so like COOET. And this part is coming from the Gignard, and the TMS group containing OR group, amino group containing, phosphoryl containing, and this the triple ester, so triester is present. So the starting material will be CO2ET, CO2ET and CO2ET. So chiral center will not be disturbed in this reaction. So 3-cyclopropane ring is formed. Gignard scope cis geometry in the absence of chelating groups. So this kind of Gignard you have to use, these 2 carbon will be there, so the olefin formation will happen. And now if you use this, so this starting material will be ET, this magnesium bromide suppose, plus CH3COOET. So these 2 will give you this product, and this will be 2 equivalent. Also this one, this is this kind of phenyl ethyl magnesium bromide suppose, then alpha beta unsaturated, here also functionalized, this is acetal motif. So this also is tolerable under the reaction condition. So this is a chemical review 2000, there the all details are discussed. Now what will be the mechanism? So the mechanism also involves, like earlier, the titanocyclopropane dialkyl diisopropyl oxotitanium complex. Okay, this was the mechanism. First the two alkyl groups comes from the Gignard reagent, this one is formed, and after that elimination of this alkane you get this titanocyclopropane. So this is very important, titanocyclopropane. So titanocyclopropane is formed, and now the insertion of the carbonyl group of the ester in the weakest carbon titanium bond leads to an oxo-titanocyclopentane 2. So this is formed. So the weakest means this less substituted carbon titanium bond breaks, and you get this. And this oxo-titanocyclopentane being rearranged to ketone, of course here this OR3 group will eliminate, minus OR3 group will eliminate, you get this, or it will bind to titanium also, and a ketone will form here. Lastly, the insertion of the carbonyl group of 3 in the residual carbon titanium connection forms a cyclopropane ring. So after this bond will break. So what we have seen here, that this titanocyclopropane, the both bond will break. So first this bond is breaking to add to the esters, and lastly the second carbon titanium bond will break, so that the cyclization will happen, and you get this, the cycle again happens, the displacement by the Gignard to generate this active titanium complex. This of course acidic workup, you get this. And this is also important that both group are cis to each other, so cis compound is formed, and agostic interaction stabilization between the beta hydrogen and the R2 group and the titanium atom was called upon to explain the diastereoselectivity observed. So this is very important, this is very much diastereoselective reaction also. So the cyclopropanol is formed as one isomer, and mainly the cis isomer is formed because of the agostic interaction. Ligand exchange of titanocyclopropane with other added alkenes, this is very important because many times the Gignard reagent formation is not easy, then you can use alkene and then the exchange could be possible. Like here styrene 2 equivalent with ethyl acetate, ethyl magnesium bromide 2 equivalent, titanium isopropoxide, this is catalytic ammo reflux, 42% yield of 98:2 cis trans. So these two groups are cis to each other, and as you can see the styrene motif is here. So the ligand exchange happens. Yeah, this is the mechanism, the titanium isopropoxide to ethyl magnesium, you get this one with one molecule elimination of this C2H6 ethane, you get this titanium cyclopropene, and now the styrene comes, styrene eliminates the olefin. So, because this one is in equilibrium with this, so that proves that ligand exchange is possible. After ligand exchange, you get this styrene motif. So, phenyl substituted titanium cyclopropene is formed, and now this carbon titanium bond will break first to this addition, and then the cyclization will happen to get this cyclopropanol. So, this ligand exchange is very much important. This was published in 1993. However, for other alkene olefins, ligand exchange not fast enough, and better results with stoichiometric titanium and isopropyl magnesium X. Instead of ethyl, you can use isopropyl, also N-butyl, cyclopentyl, magnesium and cyclohexyl. So, these are most useful, that we will see in the next slide, because it has to be this complex formation. So, this should be more stable than this. However, this equilibration is not always fast, like some olefins fail to exchange, as for example 1-heptene ethyl vinyl ether, likely due to unfavorable equilibrium. And what could be the solution? The solution will be strained precursor from cyclopentyl or cyclohexyl Grignard. Like here, if you put this titanium isopropoxide with this one, cyclopentyl or cyclohexyl magnesium bromide, you get this. And now this equilibrium will be faster. So, this cyclopentene elimination will be much faster, and this reaction will be in the forward direction, the exchange will be in the forward direction. Like this one, a chiral olefin. So, this is a chiral olefin, and if you see the structure, there are 3 olefins, motifs are present. And now with this condition, with ethyl acetate, cyclohexyl magnesium chloride 4.5 equivalent, titanium isopropoxide 1 equivalent, only this terminal olefin reacts and you get this product selectively in 42% yield. So, what happens here? The exchange happens with cyclohexyl magnesium chloride. First this complex will form, then this olefin will react here to generate this substituted titanium cyclopropane, which reacts with the ethyl acetate to generate this cyclopropanol. This was published in JACS 1996. Now, intramolecular variant also is possible. So, here ester and olefin in same molecule. So, this exchange can be exploited particularly for intramolecular version, because here the Grignard immediately react with the ester. So, for this system intramolecular variant, only ligand exchange will be useful. So, here you can react titanium isopropyl magnesium chloride to get this, and now this complex which form titanium cyclopropane, the bond which is close to ester, that bond will break. So, this bond will break first to generate this, and now the elimination of ethoxide, this is substitution will happen. This carbon titanium bond will attack here to eliminate ethoxide to generate this cyclopropanol. And this method has been used for a variety of bicyclic cyclopropanols, like this kind of system, bicyclic cyclopropanol. Here the X can be carbon, nitrogen, N can be 0, 1, 2. 0, 1, 2, so it can be cyclopentane, cyclohexane, cycloheptane. Like this example, you can see 75% yield of the cyclohexane. This is fused system 94, this is 98% yield, and this is 88% yield. So, different kind of bicyclic cyclopropanol can be formed, and these are the papers JACS 1996 from Cha group, Sato group 1997, also 1996. Asymmetric Kulinkovich is also possible, and here you have to of course use a ligand, and Corey group use this Tadol derivative. So, with ethyl acetate, phenyl ethyl magnesium bromide 2 equivalent, titanium 0.3 to 1 equivalent, room temperature 3 hours, and with this titanium complex, so which is 0.3 to 1 equivalent, stoichiometric amount or 30 mole %, and this AR35B trifluoromethyl phenyl. So this is the Tadal derivative, and you can get 64% 78% E to generate this cyclopropanol. Here also the cis stereochemistry is maintained. This was published in JACS 1994. And another variant was developed where the vinylogous ester has been used in this Kulinkovich reaction. So this is called vinylogous ester, because between this there is a double bond here, as you can see here, and if you put this Gignard with titanium isopropoxide in toluene as a solvent, then the cyclopropanation happens. So not cyclopropanol, so this is cyclopropanation. So we will see the mechanism, and this becomes ketone. Alternatively, if you use coordinating solvent like THF, so THF is coordinating, that we will see in the mechanism also. This is coordinating solvent. So in coordinating solvent, you get product like this, and if you put D2O, then this deuterium comes here. This is the enone compound, substituted enone, beta substituted enone. This was published in Organic Letters 2004. So the mechanism will be for this formation, first this, the titanocyclopropane, so this R, titanocyclopropane reacts like this way to the carbonyl group. This carbon titanium bond will break to give this 5-membered ring here, and then with Lewis acid you get this. So this happens, isomerization here, and this bond breaks. So alkoxy group is breaking here, and that is going to carbonyl with titanium. And now this one will cyclize. This carbon titanium bond will break, and this will add here, because this is now electrophilic carbon. This carbon titanium bond will break, so you get the cyclopropanation, and this double bond will be here. Alternatively, if you use coordinating Lewis basic solvent such as THF, then what happens? This coordination happens with THF, and this becomes stable. So this becomes stable, and after D2O only it breaks. So this oxygen titanium carbon titanium bond will break, and you get this tertiary alcohol. This is tertiary alcohol, this form. So in non-coordinating solvent the cyclopropanation happens, but in coordinating solvents the intermediate gets stable, and then the hydrolysis of this intermediate gives the tertiary alcohol. So this tertiary alcohol, if you put acid, then the hydrolysis will happen, that this enol ether will go to carbonyl, because it will deprotect first enol and then tautomerization. Water will eliminate because there is a hydroxy group. So water will eliminate, you get a double bond, that is the alpha beta unsaturated ketone. De-Mazery modification, De-Mazery also develop a modification, and that is using amides. We will see the tertiary amides only. So if you have a tertiary amide with identical condition, ethyl magnesium bromide 2 equivalent and titanium isopropoxide 1 equivalent, ether solvent, after that acidic vapor, you get this cyclopropyl amine. So this is the mechanism, that here also titanocyclopropane is formed, and this happens, the addition happens to the amide. And now if you have a tertiary amide, then this nitrogen is more Lewis basic. So this nitrogen will push electrons to break this carbon oxygen bond, and after this breakage, then the carbon titanium will attack to the iminium. So this is iminium ion, because there will of course a positive charge here, and this iminium ion on cyclization give this cyclopropyl amine, and this will eliminate. So this method requires stoichiometric titanium isopropoxide for useful yield, because this is the formation from titanium isopropoxide. Diastereoselectivity is generally lower than with esters. Can use ligand exchange to generate active titana cycles, that we will see. Disubstituted alkenes and cycloalkenes react. Can easily access primary amines by catalytic debenzylation, that we will also see. That tertiary amine you can do if it is a benzyl group, easily with hydrogenation condition you can debenzyl. So these are the scope of this reaction. So here you can see this coming from the amide. So this OMe NBN2 is the amide. Here also this is the amide part. So you have to put a carbonyl group, and this is of course the ligand exchange, that we will see. This also ligand exchange, this ligand exchange. This was the amide, and here also this was the amide. So HCO NBN2 formamide is the, here you get 26% yield, and the reducibility is not good. So this is the ligand exchange that we are telling. This was the formamide, and this is the 5-membered as a cycle. This will do the exchange, because titanium isopropoxide is 1.2 equivalent, and this is the Grignard. So here the cyclopropanation will happen with this cyclohexyl magnesium chloride 2.5 equivalent. As we have seen, this will eliminate like this cyclohexene. So the ligand exchange will happen, you get this one, the product. This is the bicyclic amine, bicyclic tertiary amine is formed, which under hydrogenation condition H2 palladium charcoal you get a primary amine. So this becomes primary amine now, and this kind of structures are present in many natural products, such as this compound. This is antibiotic compound trovaloxacin, Trovan. So you can see this motif is present, and this motif can be easily obtained from this Mejiri variant. So this is Mejiri variant of Kulinkovich, and here the ligand exchange happened, so that you get this one bicyclic compound in 87% over 2 steps, greater than 2:98 dr. So here for this case the diastereoselectivity is good, and cis compound is formed. So cis compound. Now we will see the reaction with nitriles. So this is called Simoniac variant. With nitriles you get this 5-membered titana cycle, and with BF3 what happens, this imine generally will not cycle, because this imine is not activated enough so that this will attack. But if you put BF3, then the cyclization will happen, because BF3 will activate the iminium ion, and the cyclization will happen to generate the cyclopropyl amine. Cyclopropyl primary amine you get directly here. Earlier we have seen tertiary amine was forming, here primary amine. If you do just hydrolysis, you get a carbonyl, because this imine gets hydrolyzed, and if you put ethyl magnesium bromide excess, then you get ethyl addition also to get a amine. So this is quaternary center. Quaternary center is formation happening. This ethyl is present already here, and another ethyl coming from the Grignard. This was published in ChemCom 2001. This is very important, that nitriles variant of the Kulinkovich reaction. Now we will discuss titanium 4 chemistry. So first, titanium 4 mediated addition of nucleophiles to aldehydes exhibits excellent stereo control. The attacking nucleophile is either ligand of the activating titanium complex or an additional reagent. The stereoselectivity results from the bias of titanium center, for example, asymmetric allylation of aldehydes and in reaction mediated by chiral titanium complex provide the corresponding homoallyl alcohols with excellent enhanced selectivity. Like here, this is the overall reaction, the titanium complex that can activate, because this is Lewis acid also. So, it can activate carbonyl compound, and this nucleophile can be internal from the titanium which has bind to titanium. We will see like allylation, you get this compound, the addition product, and external nucleophile like in reaction we will see you get this product which nucleophile is adding outside. This example is in reaction we will see, and this is allylation reaction. So, this is the allylation. So, in this case actually the trans was used, or trans allyl lithium, and this is the Tadal derivative with titanium. You can see here one chlorine is there, of course, which will be displaced by this lithium to get this intermediate. And now if you react, this is a chiral allyl titanium. Chiral allyl titanium is formed here. And now if you react with aldehyde, after workup you get this product. So, this is anti product is forming, anti product in 95 to 98% E. R dash can be alkyl, aryl, allyl. So, different substances can be tolerated. Also this is Tadal based, and this is bienal based. Bienal based, what happens, the formation is little bit tricky. If you put titanium like Y is equal to hydrogen, is bienal, titanium isopropoxide this, but you get very less yield. This is but E is good, and also dry molecular sieve also the yield is not good. Also with this one titanium chloride you can get a product, but the E is dropped here 53%, 31% yield. And it has been found that if you use wet molecular sieve 4 angstrom with titanium Cl2OI PR whole 2 of course, you get this binary titanium active catalyst better yield. So, like this you have to use wet molecular sieve or water, wet molecular sieve is important, and then you get this binary titanium active catalyst, and this active catalyst then you can use for in reaction. So, this is the in reaction. This is a double bond and this is the keto ester, and this addition is happening. So, this hydrogen will add to carbonyl, that is called in reaction, and you get this product in 97% yield and 98% E. So, this is a very useful reaction. Now, we will discuss McMurray coupling. McMurray reaction is an organic reaction in which two ketone or aldehyde groups are coupled to an alkene using a titanium chloride compound such as titanium 3 chloride and a reducing agent. The reaction is named after its co-discoverer John E. McMurray. The McMurray reaction originally involved the use of a mixture of titanium Cl3 and lithium aluminum hydride, which produces the active reagents. Related species have been developed involving the combination of titanium Cl3 or titanium Cl4 with various other reducing agents including potassium, zinc and magnesium. We will see the mechanism with magnesium. This reaction is related to the pinnacle coupling reaction, which also proceeds by reductive coupling of carbonyl compounds. So, this is the reaction, two carbonyl compounds with titanium chloride Cl3 or Cl4 as well as reducing agents. So, reducing agent like lithium, sodium, magnesium, zinc, lithium, aluminum hydride, zinc, copper couple to generate the olefin. So, this is olefin is formed like pinnacle coupling here, and the reductive coupling can be viewed as involving two steps. First is the formation of pinacolate complex step, which is equivalent to the pinnacle coupling reaction. So, this is from titanium chloride zinc copper couple. This ring is from 3-member ring, and now the carbon carbon bond formation will happen. So, like pinnacle coupling to generate this one, which if you put zinc copper, then 1 chlorine will displace, it will be 2 chlorine here, and this will elimination. The second step is the deoxygenation of the pinacolate, which yields an alkene. This second step exploits the oxophilicity of titanium. So if you heat, then this elimination will happen and you get the olefin. So this step is very important. This is the carbon-carbon bond formation. Where this so this carbon or titanium bond will break, this can attack to the carbonyl and you get this intermediate. Cross McMurray coupling also is possible if you use two different aldehydes like this and this aldehyde, then with Sp2 titanium chloride and with manganese 8 equivalent THM reflux, 77% yield of this product. So this is very important and you get this trans product in 77% yield. This was published in JACS 2010. So this mechanism with manganese is described here, though this is an homo coupling to get this trans olefin here also is forming. So what could be the mechanism? Now Sp2 titanium Cl, Sp2 titanium Cl2 with manganese, it becomes manganese chloride and it becomes titanium 3Cl. So this is the active reagent. Now it reacts with the aldehyde to generate this carbon-carbon bond formation happens here, and again the manganese comes, manganese becomes oxidized to MnCl2, titanium 4 becomes reduced to titanium 3 like this, then the elimination happens and generally the trans product is formed, then this is formed, this again reacts with a TMS chloride to generate this Sp2 titanium Cl2. This was published in JACS 2010. Another reagent which is Tebe reagent, this is very useful reagent for conversion of carbonyl compounds to double bond CH2 like Huttig reaction. The Tebe reagent is the organometallic compound with the formula C5H5 titanium CH2 Cl Al CH3 This is the structure and you can see there is a bridge CH2 as well as bridge chlorine is there and two atoms are present, titanium metal atoms, titanium and aluminium are there. It is used in the methylation of carbonyl compounds, that is converts organic compounds containing R2CO group into the related R2C double bond CH2 derivative. It is a red solid that is pyrophoric in the air and thus is typically handled with air-free techniques. It was originally synthesized by Fred Tebe at DuPont Central Research. Tebe's reagent contains two tetrahedral metal centers linked by a pair of bridging ligands. The titanium has two cyclopentadiene rings and aluminum has two methyl groups that we can see in the structure, and the titanium and aluminum atoms are linked together by both a methylene bridge. We have seen already chloride atom in nearly square planar geometry. Tebe reagent was the first reported compound where a methylene bridge connects a transition metal and a main group metal aluminum. So the preparation we will see first. The Tebe reagent was prepared from this. This is commercially available. We already discussed in the initial slide. The Sp2 titanium chloride is commercially available and that you can react with trimethyl aluminum, which is commercially available to generate methane, and this is the Tebe reagent Sp2 titanium CH2L Cl CH3 and this is the byproduct LCH3 Cl. Examples, you can do different carbonyl compounds can be olefinated with this Tebe reagent like aldehyde. So this is the active species Sp2 titanium double bond CH2 which is formed to generate. So this we will see in the mechanism also. You get the olefin aldehyde to alkenes, ketones. So this is aldehyde, then ketones to alkenes is also possible. Then esters, if you have ester, if you put this Sp2 titanium double CH2, that is the Tebe reagent, ester to enol ether. So this is not possible with Huttig reaction. Huttig. So this is very important that if you have ester, you can get enol ether with this Tebe reagent and also amide. This is also not possible with Huttig reagent. So, if you have a amide with TB reagent, you get this enamines, that carbonyl becomes double bond CH2. So, these are very useful reaction. And what could be the mechanism? The TB reagent itself does not react with carbonyl compounds, but must first be treated with a mild Lewis base such as pyridine, which generates the active Strock carbene, that is the double bond CH2. So, this is formed, this is the Strock carbene, this is the active species, and it will break like this. And analogous, also analogous to the Huttig reagent, the reactivity appears to be driven by the high oxophilicity of titanium 4. The Strock carbene 1 reacts with carbonyl compounds to give a postulated oxa-titanocyclobutane intermediate, like Huttig reaction, oxaphosphate, here oxa-titanocyclobutane. This cycle intermediate has never been directly isolated, presumably because it breaks down immediately to the product to produce the desired alkene. So, this is the reaction, Strock carbene reacts with the carbonyl to generate this cycle, oxa-titanocyclobutane, and this. So, you can think that a double bond titanium double bond is forming and the olefin is generated here, like Huttig reaction. And in Huttig reaction you get the phosphine oxide, here you get the titanium double bond oxide and you get the olefin. And lastly, we will discuss NEF reaction, that is also powerful reaction to convert nitro compounds to carbonyl, and we will see that is the McMurray variant. Conversion of primary or secondary nitroalkanes to aldehydes and ketone, a McMurray modification using titanium chloride in water glyme. So, this is glyme's structure. So, in water glyme and titanium chloride, also the pH is important, pH has to be below 7, then you can get this nitro to carbonyl. Also, if you have alpha beta unsaturated nitro compound, then also it goes to carbonyl compound. And what could be the mechanism? So, with base or acid, you get this isomerization to get this N oxide, and now titanium chloride pH 5 to give this intermediate, which goes out to give this oxime. So, this is very important, it goes via oxime, and this oxime again in presence of acid you get this imine, because this imine without substitution is not stable, and immediately with water it will go to the ketone. So, NEF reaction is a powerful reaction for the conversion of nitro compounds to carbonyl compounds. This was published in JOC 1973, 38, 4367 is the page number. So, today we have discussed the titanium based reagents. First we have discussed titanium 2, and we have seen the Ziegler-Natta catalyst, where the olefin is converted to a polymer compound with this Ziegler-Natta catalyst. That is a very useful reaction, and Ziegler-Natta got the Nobel Prize. Then we have seen the Reppe reaction, and in the Reppe reaction we have seen the 3 alkynes can be used. 3 alkynes gives the benzene derivatives. Also we have seen the nitrile variant, and with nitrile we have seen that you can generate pyridine, also you can generate pyrrole. When 2 equivalents of nitriles are used, then pyrrole is formed, and if you use the benzaldehyde or aldehyde derivatives, then you get the furan. And then we have seen the titanium 2 chemistry for the cyclopropanol formation, which is called the Kulinkovich reaction, and in the Kulinkovich reaction an ester is converted to cyclopropanol if you use 2 equivalent of Grignard, and this method is very useful. The product is formed selectively, also cis product is the major product. Then we have seen the variant of Kulinkovich, that is the asymmetric variant. We have seen that titanium Tadal complex can give the asymmetric product, and also we have seen the vinylogous ester also can be used, and you can get different products depending on the solvent. If toluene is there, then you get the cyclopropanation. On the other hand, THF you get the alcohol product. Also we have seen the de-Majory variation, that in the de-Majory variation the amides are used and tertiary amides are used. That case you get the cyclopropyl amine, and this N-benzyl group can be deprotected with palladium hydrogenation condition, you get the primary amine. And this also we have seen that in here the diacetyl selectivity is a little bit less, and like Kulinkovich reaction, here also ligand exchange is possible and different olefins can be used to give this bicyclic cyclopropyl amine. Then we have seen the reaction with nitriles, and nitriles with Grignard, we have seen that if you use BF3 then also cyclopropyl amine is formed. Alternatively, if you hydrolyze you get the ketone. Alternatively, if you use the Grignard reagent you get a amine, primary amine with a quaternary center. And lastly, we have seen the reaction of titanium 4, and here the addition to aldehyde derivatives we have seen, also the asymmetric variation we have seen, the internal nucleophile like allyl you can give the product in high yield. Also we have seen the external like in reaction we have seen that you can get the high energy selectivity for the product. Then we have seen the McMurray coupling, carbon-carbon bond formation, and a olefin is formed, and the mechanism is similar like pinnacle coupling. And here a reducing agent is used like lithium aluminum hydride, manganese, magnesium, and zinc copper coupled to give this olefin. Then we have seen the NEF reaction. In the NEF reaction we have seen the nitro compound can be converted to carbonyl compound, and this is also an useful method. Here the titanium chloride and diglycine is used, and under this condition the oxime is an intermediate and you get the carbonyl compound in very good yield. Thank you.